Hi, I'm Edgar Migueles Pérez, and my advisor is Luis Octavio Silva Pereira. I'm going to talk about analytical sampling in spaces arising from Jacobi operators. Okay, introduction. The analytical sampling theory is used to reconstruct functions from their values in a discrete set of points in their domain. So we need the following definition. Definition: points where a function is evaluated are called sampling points, and samples are the values taken by the function when it is evaluated at sampling points. Okay, this theory has several applications both in engineering and science. The analytical sampling theory is related to other areas of mathematical analysis, such as approximation theory, harmonic analysis, etc. There are classical results in analytical sampling theory for a particular class of spaces, the PW spaces. In the PW spaces, we have sampling, oversampling, and undersampling. These results are known as Cramér-Lagrange interpolation formulas. Intuitively, the oversampling consists of considering a dense set of sampling points to make the reconstruction more robust. On the other hand, the undersampling permits that the error in the reconstruction to be estimated when the set of sampling points is less dense. Okay, begin with classical results. Paley-Wiener of type A space, for short PWA, can be defined via the Fourier transform of function whose support is contained in a finite interval centered at 0. That is, given a greater than 0, the space PWA is this set. Okay. A basic result is the Paley-Wiener theorem. Paley-Wiener theorem says that Paley-Wiener spaces can be considered as the set of entire functions that are integrable square in the real line, and these functions are bounded by this function. This theorem is important because this is a complete characterization of DB spaces. Well, basically, the reconstruction of function in Paley-Wiener spaces can be divided by three parts. Number 1, sampling. Number 2, oversampling. And the last one, undersampling. Okay, the first case is sampling. Here, the sampling in Paley-Wiener spaces can be summary in the following result. The Whittaker-Shannon-Kotelnikov's theorem says that all function f in PWA can be written as this expression, where the function GA is sine AC minus t divided by AC minus t. Here, the series is uniformly converged in compact subsets of C. Note that the function g depends of two variables, c and t. Also note that the information about the function f is contained in a countable set of samples. Okay, observation: if 0 less than a less than b and less than infinite, Then for each function f in PWA, and this set is contained in PWB, then the function f can be written by this expression, and the function GA is this function. Also, f can be written by this expression where the function GB is sine b c minus t divided by b c minus t. Note that the functions g are distinct due to a and b. Also note that the distance between each pair of points in this set is greater than distance between each pair of points in this set. Okay. Due to above, the following results can be shown. Oversampling. Let f be a function such that f is in PWA and this set is contained in PWB. Here a less than b. Then oversampling consists of finding a function g tilde. We call this function sampling kernel, which depends of the I and b, such that f can be written by this expression in such a way this reconstruction is more robust against errors. Okay, this means that if epsilon given by this series is in L infinite, and we define f epsilon by this expression, then the function absolute value of f minus f epsilon is uniformly bounded in compact subsets of C. Modifying the sampling kernel allows us to obtain a more stable analytical sampling formula under perturbation L infinite on the samples f np divided by b. Okay, we now proceed with undersampling. In this case, the objective is to approximate a function f in PWB minus PWA using another one function f tilde given by this expression, such that the function absolute value of f minus f tilde is uniformly bounded in compact subsets of C. Okay. In this talk deals with the subject of an analytical sampling for functions that belong to certain spaces arising from operators called Jacobi operators. More about this in a moment, which belong to a special class of operators that we denote by S1H after we define S1H. H. We want to obtain results analogous to analytical sample in polybinar spaces. Okay. The branches space. Begin with some definition. Axiomatic definition of the branches space. Let H be a linear space of entire functions. We call H an algebraic the branches space if it contains a function which does not vanish identically and satisfies the following properties. Number one, if f is in H and W is a complex number not real and W is a zero of f, then the function f divided by C minus W is in H. Number two, if f is in H, then the function F sharp defined by this expression is in H. A Hilbert space H is a reproducing kernel space if their elements are function, and for H, W in C and H, F in H, the evaluation functional omega is continuous. Okay. Definition of the B space. Let H be a Hilbert space whose elements are entire functions, and H is not trivial. We say that H is a the branches space, for short DB space, if H is an algebraic the branches space and has the following additional properties. Number one, if F is in H and W is a complex number not real, and W is a zero of F, then the equality is for this equality is fulfilled in H. Number two, if F is in H, then the norm of F sharp is equal to the norm of F in H. Number three, the space H is a reproducing kernel space. Okay, remark. In a reproducing kernel space H, due to the evaluation functional is continuous, then there is a function kw in H such that for any f in H, then fw can be written by this expression. This expression is the product between kw and f. This function kw is known as reproducing kernel of H. To be clear, we assume that all products here mentioned are entilinear in the first argument. Okay. Now we define the operator of multiplication by the independent variable in B, which we denote by S. And this operator is defined as this expression. To refer to this operator, we will simply say the multiplication operator. For summary, we mention this important result about the operator S. Proposition. The operator S is closed, regular, symmetric, and has deficiency indices 1, 1. We briefly recall this definition. Okay, here is what it means to say that the operator A is regular, the operator A is closed, the operator A is symmetric, and the definition of deficiency indices. Okay. Functional model for S1H. First, we mention some key facts. S1H is the set of all operators that are regular, closed, symmetric, and have deficiency indices equal to 1. Remark, if S is the multiplication operator in the DB space, let's say B, then S is in S1B. Okay, proposition. The spectrum of every canonical self-adjoint extension of the operators that belong to the class S1H is discrete. We will make use of this property to obtain analytical sampling. Okay. Remember that all this is to construct the functional model for S1H. So we need some results. Proposition. If A is in S1H and J is a conjugation that commutes with all canonical self-adjoint extension of A, then there is an entire function C that it depends of A such that this function have three properties. Number one, the function C is zero free and the function C is entire. Number two, C is in kernel of A adjoint minus C for all complex number. Number three, C is equal to C conjugate for all complex number. So using the function C and that we have mentioned before, we can define the map C as follows. If phi is in H, then C phi C is equal to the product between C conjugate and phi on H. Okay, so we can show the following proposition. Proposition: the space H hat is a DB space equipped with this inner product. Okay. Some properties about the operator S are summarized as follows. For example, the image of A under this map is the operator S. Okay, all these properties are important for what follows. Okay. So, using above, we have the following important results. Fix A in S1H and consider a canonical self-adjoint extension A val of A. Then, for every f in H hat, then the function fw can be written by this expression. Here, the series converge uniformly in compact subset of C. Okay. I want to mention that there are recent results about DB spaces. For example, the following one. This proposition is important because here a full characterization of the DB spaces is provided. These formulas are known as Lagrange formulas. Okay. We now proceed with Jacobi operators. Well, the principal concept in this talk is the Jacobi operator. First, we define the G now operator. The domain of G now is L-fin n, and this operator is defined by this expression star. This expression is a recurrent relation. Hence, we define the operator G now adjoint given by star, which is defined on the maximal domain. So, the Jacobi operator, normally the Jacobi operator is denoted by J, is defined by this expression, that is J is equal to G now conjugate, or G is equal to G now W star. I forgot to mention that L fin n is the space of all sequences on n with finite support. That is, sequences that are eventually zero. Okay. From recurrent relation mentioned in star, the first kind polynomials corresponding to J are constructs and will be denoted by P naught, P1, etc. So we can construct this vector PC is equal to P now, P1, P2, etc. This associated vector has properties as the xi function with respect to J, and it allows us to construct the functional model for this operator. Okay, namely, we define this map C J phi C is equal to the product between P C conjugate and phi on L2N. The space Pj denoted by this expression, accurate with the inner product given by this, is a dB space. So we arrive at the following result. Theorem: the spaces Bj are precisely those dB spaces in which the polynomials are dense. Okay, let's continue. Remark: the reproducing kernel of spaces Bj has the following form: KWS is equal to the product between PC conjugate and PW conjugate on L2N, where PS is the vector of first kind polynomials associated with J. That is, P is equal to this vector as previously mentioned. Okay. We now proceed with stability of the spaces arising from Jacobi operator. When the spaces are arising from shortening operators, Remlin or Bessel, Silva and Tolosa, the sets of functions that are in the spaces present stability. Now, what is the stability? A space arising from an operator present stability if when the operator is perturbed, then one has another space with the same elements that the original space. Okay, we have a conjecture. We think that we have stability in these spaces if one imposes certain condition on the potential. Okay, well, in this part we want to obtain results similar to sampling in Paley-Wiener spaces or the spaces arising from Schrödinger operators, but there is a difference because here we don't use a change of subspaces. Okay. Theorem: sampling. Assume that A is in Bj and A ball is a canonical self-adjoint extension of A. Then, for every phi hat in Bj, then phi hat W can be written by this expression. Here, the series is uniformly converged in compact subsets of C. If we define G by key lambda W divided by k lambda, then the function C hat W can be written by this expression. This expression is more short. Okay. As we mentioned earlier, oversampling and undersampling in PW spaces and spaces arising from shorting operators are based on chains of subsets. However, in Jacobi operators, only properties related to the theory of the moment problem are used. Okay. Finally, oversampling or robustness. Really, we don't have oversampling because we not work with chains of subspaces, so we have robustness. Okay, theorem for phi hat in Bj, and if we have epsilon is given by this series in L infinite and define phi hat epsilon by these expressions, then the function absolute value of phi hat minus phi epsilon hat is uniformly bounded in compact subsets of C. So this theorem can be considered as robust analytical sampling in spaces arising from Jacobi operators. So we have robustness in spaces arising from Jacobi operators. Okay, that's all. Thank you.